of presenters and presentations. As I mentioned, we have a series of talks. The first set of talks is going to be presented by Alexis Del Rio and Praveen Ramachandran from our European team. Alexis is based out of the UK. He's an Adams and VTD technical consultant. His past experience include motor racing, off-highway, and aviation hydraulics. And he's done a lot of work across multiple different domains, such as racing vehicles, catamarans, and automotive OEMs. He scaled up from being a race support engineer into CAD design and engineering, and eventually into a full-time simulation engineer, which is his role currently with Adams. And in his free time, he is into motorcycle riding, yoga, and hiking. Praveen Ramachandran is based in Sweden. He's a technical consultant. He has a background in machine design. He is specifically interested in simulating mechanisms, driveline simulation, electric mobility, machine learning, and so on. In his free time, he loves to spend time exploring new cultures, hiking, and traveling. So with that said, I am going to pass you the ball initially, Praveen. And give me just a second to do that. And please unmute yourself. Yeah, which it looks like you've done. And please share your screen and start presenting, Praveen. Thank you.
Yeah. Thank you, Hemant. Thank you for the nice introduction. First of all, I will share my screen to our audience. Can you see my screen now, Hemant?
Yes, I can. Yeah, thanks, Praveen. Go ahead.
Yeah. Hello, everyone. My name is Praveen, and together with my colleague Alexis, we're going to take the first session of today's webinar. So we start with the introduction. I think past couple of years, we who works with automotive business and hear a lot about electrification. A lot of new exciting car models has been released by our big automotive OEMs across the globe. If people who have driven one of them knows that it's really exciting to drive a electric vehicle, mainly because of its enthralling acceleration, the stability that it gives because of its lower CG. So it's a really exciting time for us to be engineers, and you know, as one of the main reason or one of the main driver behind this change, this positive change, we can call it, is based on statistics, as you see in the figure below. So here, what is displayed is that, as you know, the transportation sector accounts for a large chunk of global CO2 emission, which is one of the causes of climate change and global warming. And also it causes issues like pollution in the cities. So in this transportation sector, around 75% of these emissions comes from the road vehicle. And as you know, this sector is one of the predominant uses of our software, Adams. Our colleagues feel that we have an opportunity to bring a positive change, and this is one of the biggest motive where we kickstarted this Adams EV initiative. Try to help our customers to design the best electric vehicle possible with the best driving experience possible with help of Adams. So before proceeding further, and this is just one of the way I would like to address this issue. I mean, many of us might own a car, and let's say we drive approximately around 15,000 kilometers in a year. It can change from person to person. But let's say if an average IC engine car emits around 160 grams of carbon dioxide, our car emits around 2.4 tons of carbon dioxide a year. To put that in perspective, we can say that 1 acre of forest, which is around 4,000 square meters, it absorbs 2.5 tons of carbon dioxide a year. So that's the amount of the carbon footprint of our one car. So this is so I hope this is you can see the importance of this mission personally as well. So with this, our customers, many of our customers are driving with the electric revolution, and we decided to work on it, and we came up with a few examples that will be helpful in your day-to-day work. And this is an overview. I have my colleagues, Manuel and Kent, will speak about some of the application side. But on the first session, we will speak about the new electric powertrain models, which we designed in Adams. And in this session, me and my colleagues will be taking over. So the first question is, hopefully you all are familiar with this first model, the typical Adams example assembly model. It uses an IC engine. And the first question is, how do you convert this IC engine Adams model into an EV model? And the next question was an EV model. When you convert it from an IC engine to EV model, there can be many sources of power. In an IC engine, there used to be one engine in the front, and then maybe you have four-wheel drive. You transfer the power using drive shafts to the four wheels, but you never have two engines. But in case of an electric motor, you can have two different motors, in the front and the rear. You can have four motors, like in a hub-wheel driven car, or it could be like a truck with many motors. So how to address it? Then we also will highlight how we converted from the traditional equation-based, the GSE-based powertrain modeling to a more Adams-based powertrain modeling. And we'll also highlight some of the changes we brought in the template, especially related to the communicators and how the compatibility with the STI test rig and so on. And then my colleague, Alexis, he will speak a little bit about regenerative braking, and he will show some of how this can be demonstrated. So I will start directly with the demo. So let's see. Yeah. So now you can see the familiar Adams assembly model. And then what we are interested is in the EV powertrain. So as you can see that there are two motors in the model. One drives the front and one drives the rear. And the first thing we are going to look at is the topology. So unlike the traditional GSE-based model, here everything is modeled using Adams component, which gives a kind of openness and which makes it easier for our users to modify it. So if we look at the front part, we have a housing which is attached to the subframe using the bushings, which is like the engine mounts. We have a rotor part which represents the rotational mass and inertia. We have a two-stage gear reduction. You have the intermediate shaft and then the differential, which will be used to transfer the torque from the motor to the drive shaft, which is attached here on this side. So and we are using couplers for gear reduction. So this is actually a really simple mechanical system. What we have modeled in this template is that we are using actuators. The actuators act between the rotor part and the stator part. And we have two actuators, one for representing the driving torque and the other one representing the regen torque. The driving torque and the regen torque, they are controlled using splines. So if you go to here in the spline, you can see the splines used for these actuators. And the driving torque is a function of the throttle demand and the RPM, and the regen torque as a function of brake demand and RPM. There could be other way to model regen torque, which my colleagues Alexis and Manuel will explain. But in this case, in the simple case, it's just based on brake demand. So if we open one of the example for the driving torque spline, you can see that this is really familiar. It's similar to IC engine, but you can see that how the torque varies across RPM for different value of throttle. So you have, when you have 100% throttle, how does the torque varies? And when you have 0%, how does the torque varies? So this is actually a really simple way of using splines to model a electric motor. We also have some variables which is called scale factors that can be used to scale up and down the amount of torque applied to the motor. So this is the first set of information. Now, as you can see that one of the interesting questions which our users used to have is that how do we support this multiple powertrain configuration? So let's say right now it's an all-wheel drive system. If we want to convert this into a front-wheel driven car, how do we do it? So what we have done is that we have implemented a menu-based setup for it. So what we can do is we go to adjust menu, we go to powertrain configure, and when you press instead of all-wheel drive to front-wheel drive, we can see that the rear part is disabled and only the front part is active. So as you can see that you can actually change your configuration from the standard interface. So of course you can ask a question: is it just disabling and enabling the groups? Is that all? I would say no, because what is also changed with the help of this menu or the macro is that there are some communicators which communicates the property of the powertrain to the SDI test string, the standard driver interface test string. So what we are doing is we are also changing these state variables in the background. So this is just for your information. So now we have a front wheel driven car, and as you can see, we don't need this drive shaft, the rear drive shaft anymore. So let's disable that one as well. And let's go to driveline activity, inactive, and it's gone. Then we come here, and then here we can do a standard acceleration analysis. So it's a front wheel driven. Can see, can do a closed loop throttle. So then you can do an acceleration analysis. I will not go through the analysis itself, but I will directly go to the results just to save some time. So here is a short summary of what we explained. So we have the torque, we have scale factors, we have the spline-based model, and we have made changes to the state variable, at least the macro makes changes to the state variable. And as you can see, some of the results from it. So here we have a closed loop acceleration event with the EV model. We want to have, the user want to have around 0.5 G of acceleration from 1 second. So you can see that it is doing that, and the speed of the vehicle is increasing accordingly. This is an example where we compare acceleration for a front wheel driven versus rear wheel driven vehicle. And as you can see that the throttle demand is the same for both the cases, but a rear wheel driven vehicle, as you can see in this picture, got better acceleration and resulting in a higher velocity because of the weight transfer to the rear. So if you see the drive wheels, you can see that for a rear wheel drive, the normal force on the drive wheel is higher compared to a front wheel driven vehicle. So these are some of the kind of simulations that you can do. But of course, this is compatible with most of the Adams standard analysis, and this is something you can try this out. Yeah. And of course, you can ask a question, something like, so you have created a macro. So do we need to add any additional setup file? And or if I decide to transfer this file to my colleague, do I need to send something more? Actually not. That's actually a good feature inside Adams, which is called the template macro. So this macro is actually saved inside the template, and as you can see in this image, this is a screenshot from the template file itself. The macro is actually saved here inside the template, so you don't have to send any additional file, or you don't have to. So it's very easy to use. If you're interested to see the macro, you can actually see that under the database navigator under macro mac power config. So this is a short summary of the EV models. Now maybe I will invite Alexis to show the next demo. I will stop sharing.
Yep. Hello, can everybody hear me?
Yes.
Yeah, okay, well, thank you for coming. I'm going to share some application, and let me know when you can see it, please.
Yeah, I can see it, Alexis.
Thank you. So the intention here is to show you, in case you want to tune your model during the simulation in such a way that you can review certain aspects of the vehicle, like a performance drop. And this is done fairly easy, as you may have seen through Praveen's model. Once you double click on the powertrain subsystem, you will see that there's some point torque actuators, which basically move the wheels for regenerate or drive the vehicle backwards and forward. And these actuator variables, which are basically a scale of, which are real numbers. These allow you to modify things during the simulation once you run into the event builder. But maybe if I show you the template, you will see in a bit of a better way. So the point torque, as explained, they apply the torque to the vehicle. The variables, they basically collect the value of the parameter variable here, like in this regenerated braking ratio, and it's a single figure. Then you also have your state variables, which basically give all the characteristics to the vehicle required to work. If I were to put I could have set these actuator variables inside the system elements, but then they will not be tunable during the simulation. And that's the intention here in this example. We wanted to show you that you can do this, and the way to demonstrate is going back to the standard interface. There's two ways to run this. So you could do a full vehicle analysis and do a file-driven event. And through here, you could press this button to open the event builder and then modify, or you could do it the other way around, which will be going through event builder. You will have to set either a new or open an existing XML file, which will have all the characteristics of the vehicle. And once you are in the bottom side, in the actuators, you can generate one to make sure that your vehicle perform the variation. So we can call it a braking region. Then we add it, and then from here you click in actuator, and you will have all the different actuator variables existing in this assembly. So in this case, we can get into regeneration braking ratio, and then create expression. Create expressions such as a step 5 of time, which will be simple enough to follow, and then say at time 1, my value is 1, and then at value at 5 seconds, I want it to go either to 0.5, or I want it to disappear completely and switch it off. Then from here, it's just a question of saving, and then saving and use. And what you will come up with is, again, you will go into the file-driven event menu, with the exception that here you will have the XML pointing to the one that we did in the I just showed you in the event builder, and then you go from there. Something to bear in mind, and this is important because it's a bit confusing. So if I say no, if I were to select the powertrain and then go into event builder and then create this this actuator, it will give me this warning. This only tells me that I need to be careful, and for Adams to really find out the list of actuators, I need to be in the assembly. And another thing that is also important to point out is that when you apply the actuation and you apply the step 5 function as we've shown, the value in the variable, which is actually this parameter value, will be overwritten. So anything you have there will be gone during the simulation and will be applied according to what you have defined. So that's something you need to be aware of, and it's good to know upfront. And that's everything from my side. Thank you.
All right, thanks, Alexis. So our next presenter is going to be Manuel Shen. Manuel, I'm going to pass you the ball.
Hey, Hemant.
Sorry, Praveen.
Yes.
I have, maybe I can present one more demo.
Oh, yeah, sure. Go ahead. Sorry about that. Yeah.
Okay, could you please make me the presenter?
Yeah, I can.
Yeah, thank you.
Give me just a second, Praveen.
Yeah.
Yep. So I pass the presenter privileges to you, Praveen.
Yeah.
Thanks.
Thank you. Yeah. Okay. So I will share one more demo model, and then I will let Manuel to present the regenerative braking. So this demo is about integrating control system to an Adams model. So here in this example, we have a control system model for the electric motor as an FMU, and we are going to explore how to integrate this to an Adams model. So just a second. Yeah. Before proceeding to the demo, I just want to introduce you two technical terms. One, Adams mechatronics. Adams mechatronics is nothing but a plugin which exists inside Adams. Most of you have access to this plugin, and what it does is that it eases the integration of control system by, for example, if you use mechatronics, you can save all the data, so you don't have to do this plant input and plant export every time you open an assembly and have to run a simulation. So all the data is saved inside the assembly. It can provide you an overview of the coupled system. So, for example, the e-motor, what are the connections? That's displayed easily. And one of my favorite thing is that it can handle units. So if it's a torque, whether if it's a conversion from Newton meter to a Newton millimeters, the Adams mechatronics can handle it. It has some tools like transducer signals, actuators, control system input and output that helps to do these operations. If you're interested to learn more about Adams mechatronics, there is a help file available under Adams help, standard Adams help. So please take a look at it. The second technical term I used is the word FMI, Functional Mockup Interface Standard. So it's nothing but a common standard to exchange data. It is supported by 150 plus tools. You can find these details in the website FMI. So it's basically a common way of sharing data between different softwares. And of course, Adams support it. And we decided to use FMI for this particular example because we want our workflows to be independent of control software. So you could use maybe MATLAB Simulink or EC5 or any other software, but if any software support, if your software support FMI, this workflow would definitely be directly applicable to your case. And one final point about FMI is the licensing. So do I need an additional license to run an FMU? And that is actually set by the vendors. For example, if you are using an FMU generated from Simulink, it's actually MATLAB who decide if you need a license or not. In case of our tools, for example, if you use an EC5 FMU, co-simulation FMU, you don't need any additional license. So it's included in the FMU. But if you are using an Adams FMU, then you need a license. So it's different across different vendors, and it's of course your choice. Now coming to the flow chart. So what we are planning to do is that we have a FMU model of the electric motor, and then we would like to integrate with our existing powertrain template. So in our powertrain template, we have front motors and rear motor, and we have to find out the correct value of the torque. So for example, what is the driving torque that is going to applied by this e-motor, and that is actually calculated by the FMU, which is on the right side. So what we are going to do is that we are going to first of all create a template where we integrate the FMU inside an Adams template as a control system. And then we will import this template into an existing assembly. And when we import it, this powertrain EV template will take the value from this e-motor controls subsystem. A little bit complicated when I explain it, but maybe I can show you in a demo how this could be done. So we go to the assembly here. So this is a standard Adams assembly. This is an EV template. It's a front wheel driven car, and what I have as a user in my hand is an FMU. So if I will just screen. So what I have is an FMU, which is a file which looks like this. So e-motor FMU. If you open this file, you will find out some files like model description, some binary files. So there is a DLL file for the Windows version and a SO file for the Linux version. So this is the file that I received maybe from the control system engineer. And what I do as a first step is to go to the template builder, and I will integrate this FMU as a control system. So right now for this webinar, I don't, for sake of time, I'm not going to explain how to do this, but you can watch it in the online training materials. So what we have done is that we have integrated this FMU in a separate template, which is called e-motor controls. And then you can see the corresponding inputs and outputs. So there is the input signal, throttle demand, brake demand, and motor RPM. And then the outputs are the torque values here. So the driving torque, region torque, which is used by the actuators. And then there is the max driving torque and the max braking torque, which is used by the SDI test rig. So this is how it looks like. And now what I do is I go back to the assembly, and here in this model right now it is based on the spline. And what we will do is we will import this new e-motor controls subsystem into this assembly. So we go to assemblies and we say add subsystem, and we click here. We just add e-motor controls. So now this particular subsystem, the control subsystem, is part of the assembly. And due to the way in which the assembly is modeled, now the motor will takes the value from the FMU instead of the spline. So now this model is controlled by the FMU. You can actually see or get a visual picture of how these controls are connected. So if you go to the mechatronics plugin and if you click on the signal manager, press OK, you can see the control system present here, and you can see how the connections are done. So if you look at the input channel, you can see the throttle demand is connected to the throttle demand, brake to the brake, and so on. And you can, if you go to the output, you can see that there is some output ports, but it's not connected. So I'll just show you how to connect it. So, and you can see how easy it is. So there is something called war motor drive torque. So you double click here, and you, since we are only working with front wheel driven, so you can select front motor driving torque. This is selected. Next one is motor region torque. So it's front motor region torque. Max driving torque. So that should be max front motor max driving torque. Front motor max braking torque. So you can actually double click and do the connections, and you can see that now the output channels are connected to the right signals. And then you press OK. All the information, all the signal connections are done. And when you save this assembly, all this information is saved with the assembly, and you don't have to redo this. And what you can do is you can directly go to the standard events. Let's say similarly an acceleration event, and you can just perform this event without much, just like the previous one. So you press this, and then you get the result. So that's a short summary of the regarding the Adams mechatronics and integrating mechatronics model into it. And one of the things, this is a short summary, one of the things that I would liked about this system is how mechatronics handle the control system. So what is good is that it saves all the, so this is the database. So it saves all the necessary file for the control system within the database. So there is something called, this is the database, and it saves it under external system libraries. And here you can find the FMU and then ESL file and all the necessary files. So in this way, it's actually quite a neat way of integrating control system as well. So that's a short summary of integrating control system. I hope you try this out, and hopefully it will make your life more easier. Thank you. Maybe Manuel, you can take over.
Yep. Thanks, Praveen. Yes. So let me quickly introduce Manuel, and Manuel, then you can start sharing your content. So Manuel Chen is going to talk about regenerative braking next. As Praveen mentioned, Manuel is an MSc consultant for multi-body and system simulation and Adams car expert. He has 20 years of experience in multi-body and vehicle simulations for the automotive and defense industries. He's worked on applications such as simulation of suspension, vehicle dynamics, NVH, durability, and control systems. He's got a background in controls and electrical engineering. So with that said, Manuel, I'm going to pass you the ball. Yeah, so okay. You should be able to, yep, so I see your screen. Yep, looks good, Manuel.
Okay. This one. Okay, so I'm presenting now the regenerative braking scenario you will find in the workshop, in the asset. And this scenario is using a free EZ5 control system working together and communicating some kind of information. I will explain you how this is working, how the three systems are working together. Before, I must explain, give some technical details about the co-simulation, what we call co-simulation, because the example we show here is using Adam's control, so-called external system library mode. I explain you what is exactly. So the standard and usual discrete co-simulation, as explained here, is using two solvers, solver A and solver B, and each solver is taking care of this set of equations, maybe mechanical equation and electrical equation, for example. So the two solvers are working together and communicating in a discrete steps, and this leads to a loose coupling simulation, in fact. So it's usually quite slow as co-simulation. What we are using here is what we call model exchange external system library in Adam's control. So in this case, the solver E, which is Adam's solver, is taking care of integrating the equation B of solver B, which are typically the electrical equation in this case. And here we have a single solver and a coupled set of equations, so you have a tight coupling. And this is achieved by using what we call in Adam's general state equation, which is a set of non-linear differential equation in Adam's. And this is very equivalent to the FMI model exchange mode, if you know it. So some insight about the organization of the model and the subsystem. In the model we are using here, we have a full vehicle model with specifically modified subsystem and template. We have a new template on the left, which is the ECU template and subsystem. This model is embedding the ECU subsystem and control system, which is taking care of the braking and acceleration strategy, and also a very simplified inverter and battery management. And we have also a powertrain subsystem with two powertrain for the front and for the rear. And typically here we have three control systems working together, one for the ECU, one for the front electric motor, one for the rear electric motor. And so let me clarify the way everything is working and the data flow between all the subsystems. So at the beginning, the driver is issuing some brake and throttle command. And this brake and throttle command is captured by the ECU subsystem. And the ECU subsystem at the same time is taking some information, is observing the situation of the front and the rear motor. So he's observing the velocity, he's observing also the maximum torque available, because it may vary upon the electrical condition and the velocity. And upon all this information, he's computing back electrical command to the front and to the rear motor. And if necessary, and I will show you it during the next slide, is issuing some front and rear brake demand for the mechanical brake. So I will explain you how we're splitting between electrical brake and mechanical brake. And at the end, optionally, we can also output and observe some state of charge and power information about the battery status. And one insight about regenerative braking strategy we have embedded in the ECU and VCU code. So at the beginning, we observe the ECU is observing the information coming from the electric motor and from the battery status. It is computing what is at any time the maximum electric torque available, the torque capacity, the braking torque capacity that the electric motor can generate. He compares it to the brake demand at any time. if we are braking. And typically, if we have a low brake demand, then 100% of the braking capacity can be generated by the electric brake. So we are braking purely electric. But at some time, if we are braking harder, then the system is activating automatically the mechanical brake along with the electric brake. So let's see a little bit in the EZ5 model. So the three control system are using EZ5 model. So here you have a view of the electric motor. This electric motor is defined twice. So you have twice the same model, may have a different parameter for the same model. So this EZ5 model is quite simple. You have a mechanical part here with the rotor inertia and the drive shaft stiffness, which is connecting the simple electric motor to the Adams model. And the simple electric motor, in this case, is simplified equation. And what is nice with the Adams control external system library is that we can have access to this EZ5 parameter inside Adams. So we may have in Adams dialog box here to modify the parameter of EZ5. Typically here, in this case, we have 80% efficiency for the electric motor. We have a max torque of 100 Newton meter and 50 kilowatt max power. And at the end, we have also a max RPM of 10,000 RPM, a max velocity. After reaching this velocity, we simply cut off the power. This is simulating the capacity of the electric power supply capacity in the AI velocity. Some word about the ECU and the battery management in EZ5. So in this model, we have translated the braking strategy I just explained you some slide before. This braking strategy is translated into EZ5 code, and this code is embedded into the vehicle control unit here. And from this vehicle control unit, we get information from the vehicle and wheel velocity from the Adams model, and compute back the throttle and brake demand to be applied to the mechanical brake and to the electric motor. And at the same time, this model is taking care of the simple battery management and charging and discharging the battery. And just to note also a very interesting feature in the EZ5 modeling software, that we can simulate a sample and delay in the model, so we can simulate sample the system and numerical and computer system into the model, and the effect of the sample and delay. So during the workshop, you will be able to run this model. So this is a simple EV model. You will find it into the Carll database. And typically, here you see the three components which are embedding the three control system: the front motor, the rear motor, and the ECU. So we are testing the regenerative braking strategy on the simple acceleration and brake event. Here you see the velocity profile of the simulation. So we are accelerate until 30 seconds, and after, progressively, we apply a brake ramp to apply a progressive brake input. Then here you see something interesting. We can check the electric motor behavior and limit. Here you see the maximum 10,000 RPM velocity of the motor, which is limiting the velocity of the vehicle. Here you see. And you see another effect here, which is not so obvious, but you see a small inflection in the curve, this shows the electric power limitation at 50 kilowatt. After reaching 50 kilowatt, then the torque is automatically limited to keep in the 50 kilowatt limit when we ramp up the velocity. This is typical of electrical motor, of course. Another result here we can check during the workshop is the electric motor and mechanical brake demand. So here you see the brake ramp event start at 30 seconds. And until 32 or 33 seconds, you see that we ramp up the electrical demand, which is negative. In this case, which means that negative electric demand means that we are applying a braking torque. Positive demand means that we are driving, accelerating. Then you see a negative value until the maximum capacity here. So in this region, we are braking 100% electric. And after, the system detects the saturation and activate automatically the rear brake, the rear mechanical brake, and not the front, because the front is not saturated. In this case, we define a different torque command in the front and in the rear. This is the high demand, high brake demand with mechanical brake activation. And the last test simulation we do with this model during the workshop is to compare the regenerative braking on and off function on a longer course. So we have defined and we have used the 5-kilometer Imola track course you see here on the screen. Here you see the velocity profile obtained by using a smart driver pilot for this model. So the smart driver pilot is quite interesting because it allows to drive the model with a high variety of acceleration and brake events. So here you see acceleration, reach the maximum, and then we are braking because you are reaching the curve, traveling through the curve. So this deceleration here means that we are around this point here. So to travel from this point to this point, and so on and so on. So this is quite interesting to test the regenerative effect. Here you see some result about battery state of charge, so the energetic efficiency of the system. In blue, you see the curve with regenerative braking off, and you see that the battery state of charge is always decreasing. So you are always extracting energy from the battery. But in red, you have regenerative braking on activated. So in this case, we recover some energy from the mechanical brake with the 80% efficiency we have defined in the electric model. And you see the difference at the end of state of charge. And last point I want to show you is how to compare the force in the suspension component between the two simulations. I must explain a little bit how the electric brake is influencing the suspension component force here. On the left, you see a mechanical brake situation. In this situation, we applied brake force at the tire contact patch, and this brake force is translated to the suspension upright at the center by force and the torque because of the caliper here and the disc. So this induces some torque inside the suspension and force. But in case you are using electric motor brake, you are not braking with mechanical brake, but with electric motor. In this case, if you apply the same tire patch, the same brake force at the tire patch, then you have only a force, the same force as the suspension upright at the wheel center. And at the same time, the brake torque is transferred not at this point, but it's transferred directly to the electric motor suspensions, bushings. by the transmission shaft. So you see that the effect of the mechanical brake and the electric brake is not the same on the suspension. Here we have plotted the result in the bushing, suspension bushing, the force reaction, and you see that you have a huge difference between the two simulations. You have the factor 2 at some peaks. So this means that taking in consideration electric braking may be important if you want to assess for the component durability, component suspension durability. Thank you for your attention. Maybe
thanks, Manuel.
Switch to Kent West. Kent?
Yep. Yeah, I didn't realize. I didn't know if you were going to present something more, Manuel. So next presenter is Kent West, as Manuel just mentioned. Kent manages the technical support and training materials group for Adams and EZ5. His interests are reflected in the products and toolkits that he has co-created here at MSc. So he's helped in the development of Adams Explorer, the Adams Command Server, the Adams Macro Organizer, and Adams Insight. So Kent has a lot of breadth and experience with Adams. And with that said, Kent, I'm going to make you presenter now, and let you share your screen. Give me just a second, please. Yep. Kent,
thanks.
You're the presenter now. Yep. Thanks.
Thanks, Hemant, and good day, everyone. So again, my name's Kent, and I'm going to talk briefly about the final example that we've got here, which is integrating a control system into an existing vehicle. And in particular, we're going to create a simple hybrid vehicle, and we're going to implement a simple form of torque vectoring on this system. So just in terms of background, if I could get my slide to advance, really quick background about vehicle simulations with Adams Car. Typically, engineers would be using Adams Car for suspension analyses, and you're determining some handling characteristics of a vehicle. You might then, once you've got the handling dialed in, you might want to look at ride characteristics, and then eventually noise, vibration, harshness, and durability considerations. As you need to do more of these different types of simulations, typically the model fidelity increases. So you need more detailed model description in order to do these other analyses. And so a typical thing that we see with Adams Car is that you can create quite a high fidelity vehicle model, but you don't need you have a low fidelity controller model is quite typical. So as we, in this new day and age, driver assist systems are more and more pervasive, or advanced driver systems, ADAS systems are typically more typical. But if I step back and look at what a driver assist systems are, I think everyone understands what these are. They're used to improve the vehicle characteristics for things like ABS, traction control, and electronic stability control. So typically engineers want to characterize the basic vehicle subsystem though, and the driver assist systems are employed after the fact in order to improve the vehicle response. So once again, you typically have a high fidelity vehicle model in Adams Car and a low fidelity control system. So why do we want to create a high fidelity combined system? I think everyone's probably seen these things before, right? You want to validate the assumptions about simplified components that you've used previously. So if you had a really simple control system that was modeled in your vehicle simulations, maybe you want to combine the two together and validate those assumptions. In doing that, you can easily discover interactions, or well, hopefully you can discover interactions between the two systems. And as well, with newer systems, there's many more sources of information. So there's many more sensors and sources of information. So there's more and more pressure or more and more reason to do these high fidelity combined systems. And so obviously, if you have a high fidelity combined system, it's possible to get greater confidence in prediction. So that's what this model does. This model is our standard. So this is the final example that we'll talk about today. And this is the standard front-wheel drive subcompact vehicle demo model that comes with your Adams car installation. So it's front engine, front wheel drive, and so it's a typical internal combustion engine. So what we're doing in this system is we're saying, okay, we're going to take the system as it is, but we're going to add an electric motor at the rear, and we're going to have the ability for the electric motor, we'll either do, assume this is either 2 electric motors, 1 at each wheel, or 1 electric motor in the middle with, with a drivetrain that can shuttle the torque from side to side. But we're going to assume that we can add torque at the rear wheels, and this particular model does not have a detailed electric motor. It's just a simple torque application. There's no regeneration, no motor dynamics. But what we're looking at is if you add these torques at the wheels, at the rear wheels, how does it influence the handling behavior of the system? So this would be similar to a torque vectoring system that you might see in a typical car. And as manufacturers have more flexibility to put electric motors in the front and the rear in different locations, these kinds of systems are certainly easier to implement. So in this particular example, I'm going to cheat a little bit, and I'll show you in a moment how it works. But basically, there's going to be a constant drive to the front wheels from the internal combustion engine. And what I'm going to do is I'm going to sense what the slip is in the front wheels. And so this is perhaps not realistic. In a real system, a torque vectoring system would typically look at the vehicle yaw rate, maybe the lateral acceleration and the steering demand, and those would all determine how active this control system should be. But in this model, I'm going to take advantage of the fact that I've got some things I can easily measure. So what I'm plotting here is the slip angles in the front wheels as the vehicle goes through a lane change. So the vehicle goes and it turns left in a lane change, and then it kind of steadies out, and then it turns right in a lane change. And if I compare the slippage in the front wheels, again, this is just purely the front wheels that are driven by the combustion engine, you can see there's differences between the inner wheel and the outer wheel in the turn. If I take these differences in the inner wheel and the outer wheel and I normalize them, I can get this trace, which I call relative slip. And this looks like a standard double lane change, right? So the car turns one direction and then it steadies out, and then it turns the other direction and it becomes steady again. So this relative slip trace that I've got here, it indicates which side of the vehicle is the outer wheel in a turn. And so what the control system is going to do in this case, and the control system is modeled in EZ5, I'll show you that in just a moment, but the control system is going to take a look at this relative slip, and based on the relative slip in these front wheels, it's going to apply correcting torques in the rear wheels, because this is where the electric motor system is. And so the electric motor in this case is just used as a boost torque to either enhance acceleration or enhance handling in this case. So in this example, the vehicle's turning left. So again, these front wheels have this constant torque from the internal combustion engine. And in this case, the right wheel is the outer wheel in the turn. So it's spinning faster than the inner wheel. And so if I plot this relative slip, you can see in this case, during the left turn, this relative slip curve comes down and it looks like this. The controller is keying on this, and what the controller does is it says, okay, you're in a left turn, so I'm going to provide some more torque to the right rear wheel, and that should improve the turn-in response of the vehicle. So you can see that the blue curve, which is the torque on the right rear wheel, as the vehicle turns to the left, there's a torque provided to the right rear wheel, and then later on when the vehicle turns back to the right, there's a torque that's provided to the left wheel. So once again, this is how this senses the activation call for torque vectoring is kind of cheating. It's simplified, but the idea here is to give people an idea of how you'd implement one of these systems. And so in particular, how we'd implement one of these systems, I'm going to speak about the EZ5 system in just a moment. But for now, let's take a look at the how the system was modeled in the Adams car interface. And in my Adams car model, if I go over here, again, it's my standard subcompact model, and it's got the addition of this torque vectoring control system, subsystem. So if I take a look at this, the display doesn't look too exciting, right? There doesn't look like there's anything. But in reality, what this is a subsystem where there's a torque at each of the wheels. And these torques at each of the wheels, these are fed by these actuator signals. And as Praveen mentioned earlier, we used Adams mechatronics to set this up. And the reason we did that was so it's fairly easy to swap in and out different FMUs that control all these inputs and outputs. But basically, these actuator signals are passed into these torques. These torques act right at the wheel location. Similarly, there's some outputs from the system. They're called transducer signals. And so things like kinematics of the wheel and throttle demand and lateral acceleration, yaw rate, all those kinds of things would be things that would be passed out to the control system. So the modifications to this particular system were fairly straightforward, this subcompact model. Again, we added a new subsystem in here, and we made some changes to the body, for example. So the body simply has this, a transducer signal in the body. And finally, I'll switch back to this one more time. Sorry to switch back and forth so much. But the thing that actually does the work is this control system element here. And this guy is what is the interface between the Adams model and an FMU that represents the EZ5 system. I'll show you the EZ5 system in just a moment, but basically you can specify a property file here that talks about where the FMU is. If I look at this property file, you can see that this property file has things like, okay, what's the FMU file that was used? There's also parameters in here which are quite interesting. So when I build the system in EZ5, which I'll show in just a moment, you can define parameters in the EZ5 model or the, say, MATLAB model or MapleSim model, whatever it is, the FMU that's coming in, it can have parameters that can be changed. And so these are the parameters that can be changed. So in the car interface, you can see it's fairly easy to create a property file with different parameters in here. And that's what I've done for this case here. So there's in the database, you can see that there's the standard property file, and then there's another property file called 2x. And so basically it's I'll show some results in just a moment, but it's basically the same information, and I've multiplied some things by quite a bit to see how the system responds. So it's nice that this Adams mechatronics encapsulates this interface and allows you to set up these property files. So that's quite nice. So that's the general hookup to the Adams car model. As Praveen had mentioned previously, when you've got signals in mechatronics, it's quite easy to manage them and inspect them. I won't talk too much about this, but I just wanted to point out that what mechatronics does in the background for you is it manages these signals, and it connects, this input to this torque element, this output to this output of the control system, and so on. Once you've got these things set up as signals in with Adams mechatronics, it's fairly easy then to, if you want to do a study and you want to say, what if I increase the magnitude? What if I scale the magnitude of one of these signals? It's fairly easy to put a scale factor in and then just rerun your study. Or maybe you've got some disturbances that are happening on the line. Or some delays. You can easily model these using these signals that are in Adams mechatronics. So that's the main reason that the system has all these Adams mechatronics components in it. So let's talk briefly about the the EZ5 model. So this EZ5 model was developed with an Adams car block in the middle initially, and the Adams car block has these outputs, typically the kinematics from the system. So wheel velocities, wheel slips, chassis yaw rate, that kind of thing. So we typically have these outputs from the Adams block, and then meanwhile the inputs in are typically forces and torques. That's just how the system has to work. So if I take a look at this EZ5 model, the wheel slips on the front come in here, and then these blocks compute that relative slip that I showed you previously. I then compute a torque distribution for the rear wheels based on the relative slip at the front. And then meanwhile, the system's also got some activation based on lateral acceleration. You don't want the system to come on and off when you're just in a straight line in this scenario. So this lateral acceleration would be typically something that you might take a look at, or vehicle yaw rate. And then finally, these signals come in, and there is a torque demand that comes in from Adam's car, and we do some things with the torque demand. We could have a motor dynamics in here, for example. So again, this system does not have motor dynamics. There's not a detailed motor model, but if there was a detailed motor model, you'd put it here, because the torque demand comes in, and then the motor comes out with some things, and then whether or not the system is active or not is in the final torque computation. So this model was created in EZ5. I'll just flip over to EZ5, and it looks something like this in EZ5. You configure these inputs and outputs, and then in the EZ5 system, you can export the model as the FMU that Praveen mentioned earlier. So this is the functional mockup unit. And as I mentioned, you can have these parameters in the FMU model where, this block, for example, might have some scale factor in it. These other blocks might have gains or scale factors, and you can put these all in as fixed parameters. When you do this and you export, this is what actually creates the .fmu file on disk. So it does a bunch of compilation on this thing, and it creates this thing as an FMU. So that's the EZ5 model. So how does this system actually work? Well, let's take a look at, this is a simple lane change, and the blue curve is when the system is off, and I'm just looking at the rotational velocity of one of the wheels, one of the rear wheels. So in the blue case, when the rear wheels are just they're along for the ride, then I've got a certain angular velocity. When I activate the torque vectoring system, you can see the red curve is the torque is speeding up one of these rear wheels in order to, make the vehicle yaw more or less. And then if I take my, I run a study, and I do, instead of the red curve, I do the pink curve, which is where I use larger torques, and I activate the torques sooner. You can see the vehicle response is even different. You can then, since it's Adam's car, you can go in and plot any quantity that you want. You can also look at the longitudinal slip in the same vehicle. So in the blue case, the longitudinal slip is the vehicle, the tire is just coming along for the ride. It's the rear wheel, and there's no drive on it. So the slip is negative. But then once you start adding torque to that wheel, at this instant, you can see the red curve, the slip becomes positive, and as you add more and more torque, the slip becomes even greater. What this model should have, so this model right here, what it should have on these final inputs in the torques is it should have some slip threshold, right? It shouldn't provide more torque so that the wheel is slipping. So anyway, that's how the controller influences the model. And finally, what happens with in the lane change is the same kind of thing. Let's take a look at the torques that are generated on the rear wheels. So the blue curve is the torque generated with the default controller. And then if I increase the controller to be to have more to be more aggressive and more power, then it produces, a higher torque on, this would be on, say, the left wheel, and this is the torques on the right wheel. Or did I get that backwards? I think it's backwards, actually. So this is the torques on one wheel and torques on the other wheel as the lane change event happens. So in a nutshell, we've taken this model, which is the EZ5 model. We've created it as an FMU. We've brought it into this Adams car model. And because this Adams car model has this as mechatronics components, I can then go and run the lane change events that I wanted. But not only can I run the lane change, I could go and run the, the Amola track that Manuel showed, or I could run any kind of simulation that I want. Because what happens is with the FMU implementation is that this this vehicle, I can run any kind of simulation now in Adam's car. So that's the overview of this section. Once again, it was implementing a simple torque vectoring system into an existing Adams car model. Thanks.
Yeah, thanks, Kent. So, we've run over, so I don't think we'll have any time for Q&A at the very end. But that said, I wanted to point something out. There have been some questions about how to access the models that were described in today's presentations. I have included a link to a product page in the chat window. So if you follow that link, you'll be able to fill out a form and then access the models, all the models that the team described, and try them out yourself. The recording of this presentation will be available for on-demand viewing. So while working on the models, if you wanted to reference something that was described in the presentations, you can do that as well. We will be working more on EV-related templates, applications. So there'll be more to expect on this topic in the near future, and whenever that happens, we'll have a follow-on webinar. So with that said, I do want to end this webinar for today. I see a couple of questions in the Q&A in the chat window. We'll reach out to you guys separately with responses. So thanks to all the presenters. So Praveen, Manuel, Alexis, Kent, great presentations, great content. And thanks everyone for attending, and watch out for more events, virtual events on this topic in the near future. Thank you.